In this lesson, we're going to continue modeling with sinusoidal functions. In our previous lesson, we learned how to come up with equations of sinusoidal functions given a graph. Can we do the same if we're just listed characteristics in words? So let's take a look at this first example. It says when seated, an average adult breathes in and out every 4 seconds. The average minimum of air in the lungs is 0.08 liters, and the maximum amount on average in the lungs is 0.82 liters. So if they're doing this over and over and over again every 4 seconds, this is going to give us a periodic graph. We're given one more clue, which is that suppose the lungs have a minimum amount of air at t equals 0. So when we start the timer, or we start collecting data, we'll start at t equals 0, and we're at a minimum amount of lung capacity of 0.08 liters. So the first question is to write a function that models the amount of air in the lungs. Really, we don't even need this part because the actual question is saying determine the amount of air in the lungs after 5.5 seconds. So to do this part here, we need to come up with a model. So the easiest way I find to come up with a model is to just do a quick t-chart of what's going on between x and y, and then looking at those points, we can usually easily find our a value, our k value, our c value, and our d value to make up a equation. So on our left side we'll have x, and on our right side we have y. And what is x in this situation? Well, it must be the time in seconds. And our y value, what are we measuring? It's the amount of air in our lungs. So let's start to come up with some points that we do know. One point that we are given is at time 0, our lungs have a total of 0.08 liters of air in it, and we were given that information here. At time equals 0, the lungs have a minimum amount of air, and our minimum amount of air is 0.08 liters. We also know that an adult breathes in and out every 4 seconds, so that must be our period, the length of one cycle, 4 seconds. So that means if our cycle is 4 seconds, after 4 seconds we must be back at 0.08 liters. So can we fill in the blanks from here? That means halfway in between 0 and 4, or approximately halfway, we would be in between 0.08 and 0.08. And what's going to happen in between is it's going to reach its maximum, and that maximum is 0.82 liters. If we were going to continue this pattern, after another 4 seconds, which would bring us to 8 seconds, we would be back on our minimum amount, which is 0.08 liters. In between 4 and 8 would be 6, and we would have our minimum. So now that we have that, if you need to do a quick sketch to help you, go ahead and do a quick sketch. On our x-axis we know is time, and on our y-axis we know is air in liters. And so we're going to bounce in between 0.08 liters and 0.82 liters. So at time 0, we're at 0.08. After 4 seconds, let me just fill this in. After 4 seconds, we're back at 0.08, and at 2 seconds, we're at our maximum, and it's going to continue. At 6 seconds, we're at our maximum. At 8 seconds, we're back at our minimum. And if we just connect this, we can represent the situation with the sinusoidal graph, or a sinusoidal equation. So let's start finding our a value, our k value, our c value, and our d value. Starting with our a value, we know that's just the amplitude. It's going to be the height from the middle to the top. Another way to think about that, it's the max minus the min. So 0.82 minus the min, 0.08, and divided by 2. So that gives us an amplitude of 0.37. Now let's find our k value. We know we can find our k value by first finding out our period, so the length of one cycle. Well, we were given the length of one cycle. It's every 4 seconds. So that means that if our period is 4, then our k value is going to equal 2 pi over 4, because we know the period is just 2 pi over k, so our our k value should be 2 pi over our period. So if we simplify that, that's going to be either 0.5 pi or just pi over 2. Next, let's come up with our C value. We know our C value is going to just be how high or how low, or how has the graph shifted vertically. Has it shifted up by how much or down by how much? And we know we can just measure that by finding the equation of the axis of the curve, which is the curve that's going to cut it completely in half. So we can find our equation of the axis of the curve by just taking our max plus our min and dividing by 2. So taking 0.82 plus 0.08 and dividing it by 2, finding that average, that middle number. And that's going to be 0.45. So our equation of the axis is 0.45, which is halfway in between 0.08 and 0.82. So therefore our C value must also be 0.045. And last, our D value. Our D value is our horizontal or our vertical shift. Sorry, not a vertical shift. Our D value is our horizontal shift. So now we can choose whether we want to approximate this curve with a sine curve or a cos curve. So if we choose to do cos, you could say that cos starts here and it's just shifted to the right 2, so our D value would be 2. You could also say that cos starts here at 0, but it's just been reflected in the x-axis. That works as well. So if we were to use cos, so if we were to approximate it with cos, why don't we set our D value equal to 0, and then remember that A has to be less than 0. A has to be negative. So again, cos curve normally starts up here and comes down and comes up. Well, this curve starts down here and comes up and then comes down. So therefore we can approximate this with a cos curve that's been shifted no units horizontally but just been reflected in the x-axis. If we were to use sine, sine starts on our axis of the curve and moves up to its max, down to its min, finishes back at the axis of the curve. So we can say that our sine curve were to start here and end here. Maybe that's what you see. Then what is this point right here? Well, it has to be right in between the minimum amount and the maximum amount. And the minimum amount occurs at time 0, and the maximum occurs at time 2, so this must be happening at time 1. So we can approximate this curve here in blue with a sine curve as long as we shift it over to the right 1. So that would mean our D value be equal to 1. So now we can do two different equations. So if we put it all together, instead of y, we have L, or whatever you use to represent y. And our A value is, what was our A value? 0.037. Then if we use cos, our K value is pi over 2, but our D value is 0. And so instead of x, I'm going to put t. So there's no plus anything, plus or minus anything, because our D value is 0. And then it's been shifted all up 0.45 units. If we were to approximate with the sine curve, we have our A value would be the same. We would have sine here. Our K value would also be the same. But then we're going to shift to the right 1. So we've got to put our D value equal to 1 and then up 0.45. One last thing is to make these equivalent, or to make these both represent. Don't forget that we said that D could only equal 0 as long as A was negative, as long as for this cos curve. So as long as we made a reflection in the x-axis, so we're going to put a little minus in front of that 0.37 there. Okay, so if you can't read that, it looks like a little scribble, but it says negative 0.37 cos. So now the final part of the question said the whole reason why we were doing this is determine the amount of air in the lungs after 5.5 seconds. So our T value has to equal 5.5, and we just have to come up with our L value. So we can plug it into either equations, they're equivalent, and we can check that they're equivalent by just plotting them both in Desmos and making sure that they are overlapping on top of each other. So for B, I'm just going to pick either of the equations. I was only asked to come up with one, but I came up with two. And instead of t, I'm going to put in 5.5 seconds. So I'm going to copy negative 0.37 cos of pi over 2. Instead of t, I'm going to put 5.5. Again, I chose equation number 1. If you chose to do a sine equation, that's fine too. Plus 0.45. If you picked another equation, yet on Desmos they're equivalent, then this is also going to work in your equation as well, because all of these numbers repeat over and over and over again. So I'm going to put all of this into the calculator. Make sure that your calculator is on radians. And you should get 0.7116 approximately. So let's assess if this makes sense. So this number better be in between 0.82 and 0.08, which it is. Taking a look at what's happening at 5.5, according to this, we're just about to reach our maximum, and this is definitely approaching our maximum, coming close to our maximum, so this seems like a reasonable answer. Let's try another example. So this question is about a Ferris wheel, and it says at what times is the rider 15 meters above the ground? So part A says to use a sine function specifically to model the function. So we will do that. However, we don't need this prompt. We don't need this prompt right here, because if we have to figure out a certain time or a certain height, then we need an equation. So we can even just focus on B. A Ferris wheel completes 1 revolution every 40 seconds. The wheel has a diameter of 16 and its center is 12 meters above the ground. A rider boards on the lowest point of the wheel. So that's what we can think of as like our starting point. That's where we're going to start collecting data. And at what times is the rider 15 meters above the ground? Again, we know we have to come up with a sine function. We don't even need this little thing to tell us that we need to do that. So first thing I'm going to do is make a quick t-table. And on one side, that's our x value. We're going to measure time in seconds. So I'll just put t, time in seconds. And the other side, our y value, our dependent, is our height in meters. So do we know anything about our time and our height? Well, we know we're going to start our experiment with a time of 0. And one thing that we know is that the rider boards on the lowest point of the wheel. So what is the minimum height? Let's go back and read this. A Ferris wheel completes 1 revolution every 40 seconds. So that's the length of our cycle. That's our period. The wheel has a diameter of 6 meters and its center is 12 meters above the ground. Does that mean 12 is our minimum and 16 is our maximum? Well, draw a quick sketch if you need that to help you. So we have our Ferris wheel here. And we know the wheel has a diameter of 16 meters, so the length from the top to the bottom is 16 meters. And its center is 12 meters above the ground. So that means that from the center to the ground, it's 12 meters. So how much must this little stand be that the Ferris wheel will be sitting on? Obviously, it can't be sitting directly on the ground. Otherwise, the Ferris wheel would hit the ground every time it rotated. So if the diameter is 16, and we know that the length from the middle to the bottom is 12, well, this radius has to be 8. Therefore, this little guy here has to be 4. So this one here has to be 4 meters. Again, we know the distance from the middle to the bottom is 12. We know the radius has to be 8. This little guy here must be 4. So what is that minimum height where the rider actually gets on? Well, it's got to be at a height of 4 meters. That's our minimum height. Next, we know that 1 revolution takes 40 seconds. So 40 seconds later, we're back at that minimum height. So I can put in 40 seconds later, we're back at that minimum height of 4. So what's happening in between 0 and 40? Well, halfway up, we're going to reach our maximum height. So after 20 seconds, we're going to reach our maximum height. And that's not going to be 16. It's going to be 16 plus 4. It's got to be 20 meters. We can continue the pattern once more. If we add another 40 seconds to our cycle, where we're going to be back at our minimum, so that's after 2 rotations. In the middle is 60, and in between 40 and 80, we must hit our maximum, which is 20 meters. If you need to draw another sketch, draw a quick sketch where time is at the bottom. We measure 0 seconds going to be there. So this is 20 seconds, 40, 60, 80. And we're bouncing between 4 meters 4 meters, and let's say that this one is 20 meters. Okay, the 2 really isn't coming up, but that's fine. Okay, so let's start to plot this guy together. So 0 and 4 is where we start. At 20 meters, we're at 20 seconds, we're at 20 meters. At 40 seconds, we're back at 4 meters, and the pattern goes up and down and up and down. And if we continue it, here is our sine curve or our cos curve. So it specifically asks us to do a sine function, so let's go ahead and find the amplitude, our k value, and our c value and our d value. So try to find the a value on your own and come back to the video once you've got it. So let's check your a value first. So the a value we know is going to be our max minus our min divided by 2, and that's going to be 16 divided by 2, which is 8. Now try to find the k value on your own and come back to the video once you've got it. So hopefully you got this as your k value. Our period's got to be 40 seconds. So we know one cycle lasts 40 seconds around the Ferris wheel. So if we put into our little formula, 2 pi divided by our period is going to simplify to pi over 20. So now try to find our c value, which we know is going to be the equation of our axis. Go for it. Okay, so if you calculate the equation of the axis by adding together our max and our min, finding the average, that middle number, it's 12. So that must mean that our c value must also be 12. So if I were to just also put that into our graph, our middle would be 12. And checking our amplitude, the distance from 12 to 20 is 8, and the different distance from 12 to 4 is also 8. So these two numbers make sense. Our last step is to find our d value. How much has that shifted? Well, if we were talking about cos, it'd be a little bit easier, because cos, we could say it starts here and ends here. So the starting point would mean, if we choose this as our starting point, our d value would be 0, and there'd be a reflection in the x-axis. However, it specifically asks us to use a sine function. So that means our sine graph, maybe you see it starting here and ending here. So the question is, what is that x value right here at the start of the sine? Well, if it reaches its minimum at 0 and its maximum at 20, this must happen halfway in between 0 and 20, which is 10. So that means our d value must be 10, because there was just shift to the right 10. So now we can put it all together into an equation. So let's start with h, that's our y. H at t is going to be equal to, our a value we know is 8. We have to use a sine function because it asks us for that. Our k value was pi over 20. And then our x value, instead of x, we have time. There's a shift to the 10 to the right. So we're going to put minus 10 and then a shift up 12. So there is our equation. Part B asks, the whole reason why we're doing this is because we want to solve this problem here. At what times is the rider 15 meters above the ground? Well, let's take a look at this, our little graph that we made, our sketch. 15 meters would maybe be about here. So if I put a dotted line here, let's call this 15 meters. That's our 15 meter mark. So when is the rider above 15 meters? Well, they're at 15 meters at this point here and this point here in our first cycle, and then the second cycle at this point here and this point here. So when are they above? Well, let me just put the highlighter on. They're above here and here. Maybe I need to use a different color. Let's see if I can put green on top of that. Here, oops, yep, and here. So that's when they're above 15 meters. So there's actually an infinite number of answers to this problem, because someone could technically stay on that Ferris wheel for all of their life, just going up and down, up and down, up and down. But if we were to just specify, let's say in the first cycle, when are they going to be above 15? We can plug 15 into our equation for height and see what times we get. It should be an answer that's between 0 and 20 for this guy, and between 20 and 40 for this guy. And we can figure out when they will be above that 15 meter mark. So for B, I'm going to plug in our height equal to 15. So I'm going to put 15 is equal to 8 sine pi over 20 t minus 10 plus 12, and I'm just going to isolate for t. So the next thing I'm going to do is I'm going to move that 12 onto the other side. So I have 15 minus 12, which is going to give me 3. So I have 3 is equal to 8 sine pi over 20 t minus 10. Then our next step would be to divide by 8. So I'm going to leave that 3/8. So I'm going to have 3/8 on this side, and then our 8s will cancel out on this side, and we're left with sine of pi over 20 t minus 10. So I can't get into any of these guys here. I can't move these over until I get rid of sine. So what's the opposite of sine? Well, of course, it's sine inverse. So I'm going to apply sine inverse on both sides. I'm going to take sine inverse on this side as well. And now our sine and sine inverse will undo each other. And we're left with on the left sine inverse of 3 over 8 is equal to pi over 20 t minus 10. Almost done. Now we can get rid of this pi over 20 by dividing by pi over 20, dividing by pi over 20. Simplifying sine inverse of 3 over 8 divided by pi over 20 is the same thing as saying 20 times the sine inverse of 3 over 8 dividing by pi, because we know our trick for dividing by fractions, we're going to flip it and multiply. So there it is, flipped and multiplied. And we have these two that cross out on this side, and we're just left with this t minus 10. Whoops. Sorry, we're left with this t minus 10 on this side. So can I just skip a step here and just bring that minus 10 onto the other side so we have plus 10? So we've got plus 10 on this side, and we're just going to be left with t. So all I have to do now is put this entire thing into the calculator, and we can find our values for t. Once you plug it all in, we get a t value of 12.447. So what doesn't make sense here? Well, according to our graph, we should have gotten 2 t values. I said that one would be somewhere in between 0 and 20. That's this guy. But why aren't I getting this value? This is just t1. Where do you get t2 from? Well, take a look back at our calculation here. Is there anything here that has more than one value? 20 is just 20, pi is just pi, 10 is just 10. But take a look at the sine inverse of 3 over 8. Taking a sine inverse of a ratio means that we're looking for an angle that has this ratio. Well, according to the cast rule, this ratio is positive for sine in the quadrant 1 and in quadrant 2. So our calculator is always going to give us the smallest angle, and the smallest angle being quadrant number 1. So they gave us, when the calculator found the sine inverse of 3 over 8, they gave us this angle. That was our theta. But there's another angle over here. This is our theta number 2. So I just made some space so that we can continue this calculation. So if we were to take just the sine inverse of 3 over 8 into our calculator, we would get an answer of 0.38. Let's just approximate 0.38. Let's take one extra decimal, 0.384 radians. So that's the number that our calculator put in right here. But actually, there's more than one answer to this question. Taking a look here, this 0.38 radians is this guy right here, which means over here must also be 0.384 radians. So again, doing this picture, C-A-S-T, sine is going to be positive in this quadrant and this quadrant, and that's a positive ratio, which means our calculator is going to give us this one here. That is 0.384 radians. Our calculator is not going to give us this guy here. We've got to come up with that ourselves. They have the same ratio because they have the same related acute angle of 0.384. So what is this second theta? What is this second theta number 2? So this was our theta number 1, which is this guy here, from here to here. That's going to be theta number 1. What is theta 2? Well, theta 2 would be pi minus that. Again, we've got pi radians minus this guy. So minus 0.384. And that would give us 2.758 radians approximately. So we've also got to put that into our equation. So to get our second value of t, we have to take this equation, but instead of putting 20 times sine of 3 over 8, because we know the calculator is going to calculate it at the sine inverse of 3 over 8 as 0.384 radians, let's instead replace this guy with 2.758 radians. Then divide that by pi plus 10. Again, our calculator is going to give us the smallest angle measure it can. When we punch this into our calculator, we've got to almost override it because there's a second solution to that. So we're going to change this into this value right here. So let's do it together. In our calculator, we're going to put, to find our T2, we're going to put 20 times, instead of sine inverse of 3 over 8, we're going to put this, the sine inverse of 3 over 8 that we manually found. So our second theta, so we're going to do times 2.758, divide all of that by pi, and then add 10. And that will give us our second time, so our T2. We should get a T2 value of 27.558 seconds approximately. Does this number make sense? Well, let's move this guy out of the way for a second. Let's take a look. Well, our second time is supposed to be somewhere between 20 and 40, and 27 is between 20 and 40. So the question is now, how long is he above the ground, or the person, whoever's writing, is the person above 15? Well, we're going to take time 1, we're going to take time 2, and we're going to subtract them. So all we have to do is find delta t. So let's finish off this question, and we'll put on this little square. Okay, so our change in time is going to be 27.558 minus 12.447, and that means that they're going to be above the ground for approximately 15.11 seconds. And that's our final answer.